First, I want to thank the organizers for giving me this opportunity to participate in this workshop, and also for the patience that they had with me hesitating about which talk to give. But so what I finally decided to talk about is a joint work with Tobias Barthel, and Beren Sanders. Okay. And the setup is, well, you start with a tensor triangulated category. That means that you have, it's a triangulated category with a closed symmetric monoidal structure on it, and they are compatible. And also, I will assume for now that this will be compactly generated. Okay, let me give some definitions. That will be the objects we will be looking at. So, let me say what's a fixed subcategory. So that would be a full triangulated subcategory. And which is closed under direct summands. Next subcategories I will look at will be the localizing subcategory. So that means that it's a fixed subcategory which is closed under commutes. And let me add another adjective here. It's an ideal. If it's closed by using the monoidal structure, so it's that means that if let's call it L, if when I tensor elements of L with any element of T, this sits in L, and colocalizing subcategory C. It will be a fixed subcategory, which is now it's closed under limits. And I'll say that it's a coideal if now it's closed under the OM. That's the internal OM, because it's a closed symmetric monoidal structure. We have an internal OM, and then after that OMs C. So these are the objects of interest that we are looking at. And well, there is some ways of producing localizing and colocalizing categories, which is, for example, by taking orthogonals. So you have a collection of objects, and you look at you take a collection of objects and you look at those such that ohms are 0 on one side or ohms are 0 on the other side, and you have the right element orthogonal, and then that's a way of producing localizing and colocalizing categories. So I will use some notation. So if this is a collection of objects, then I will talk about, this will be the smallest localizing ideal, which contains E, and then I will talk about the small colocalizing coideal containing E. That's the notation I will use. And then when I write this with the right orthogonal, this means that you look at the objects such that is 0, and the similar from the other orthogonal, the left orthogonal. And it turns out that this is a way of producing localizing and colocalizing categories, for example. Right? The idea is to look at localizing ideals in T, and then you have colocalizing ideals in T. You can produce them by taking orthogonals, and you want to classify these localizing ideals in a certain category, or these colocalizing coideals in another category. So the way to do it historically is to parameterize each localizing ideal with some parameters, which will be given by some function. There will be a function that a localizing ideal will assign something, will be kind of parameters. And then there is a way of reconstructing some localizing ideal from some parameters. That's the way. And the way to construct these parameters, it goes by constructing some functions into subsets of the topological space. So what the idea is to map for each localizing ideal to assign some subset of this parameter space, which we call the support of the localizing ideal, but which will be constructed at each object. For each object, we will assign some subset of X, and X is a topological space. Topological space, which will be like where the parameters live. This assignment has to be somehow compatible with the structure that this category has, with the tensor structure, with the triangulated structure, and with internal OPs. So you need some function which respects these constructions, because are the ones which are close in these subcategories. Okay? So let's say, and then this leads to the notion of a topological space, of a support function, and in this case, and we will call it cosupport function in this case. So have a topological space, and we have a function from P to the parts of X, and then this appears in work, I think already appears in work of Benson-Iyengar-Krause, and recently using in another context by Barthel-Heard-Sanders, and we'll say that this is a support function if, well, I give you some properties that need to satisfy. The first thing is that the support of the zero object is the empty space, and that the support of the whole category is X. The second one is that it's invariant under the suspension, this end functor that comes with a triangulated structure for all EPT. The third one is has to do with triangles, which time you have a triangle A, B, C, suspension of A. The support of C is contained in the union of the supports of A and B. And so these three somehow has to do with the triangulated structure of the category. Then the support of a commutative of the units, the coproduct, sorry, is the union of the coproducts, and then the last one has to do with the symmetric structure. T for all x and t. Okay, this one has to do with being close at the limits, and the last one with being an ideal. And in some sense, it says that when you construct objects in your category from some generators, using these operations, the support does not increase. It's kind of controlled somehow by the generators. And what is going to be a cosupport function?
What was your very first property there? What's the first property there on that? What's the second half of it? What's that?
The support of, T is T itself is a localizing subcategory.
Oh.
Yeah. So you would take, sorry, but I maybe I should have written like that if you have, no, but that's a good point. So I define the support of a localizing subcategory as the union of the supports of all objects.
Oh, okay.
Yeah. And then for the support, for the cosupport, the first three will be the same, but you have to changes 4 and 5 to adapt to limits and ohms, right? And then, so you have 1, 2, 3, and then 4 prime. Okay. And now I have with the cosupport function, it would be like, I don't know, I don't have to do a C kind of calligraphic here. From, again, from the category to the parts of X, and then for 4 prime, it has to do with products. And 5 prime has to do with ohm. And well, the first observation is that this property here is symmetric. S and T play kind of the same role, so you could say that this support sits in the intersection of the supports of S and T, but that's not true in this condition. So there is kind of we already observed some lack of symmetry at this 5. Okay. So the question. And examples, are given. Examples in the literature where these functions appear in different contexts. I'm just going to mention quickly some of them among many. So the first comes from the derived category of a commutative Euclidean ring. And in the case of due to Hopkins and Newman for the support, and then also Newman for the cosupport. And other examples, they come from the stable module category, or for example, the FPG, the ring of when you look at modular representation theory, when you look at modules over the field, representations over the field FP, for example, and that goes to the work of Benson-Iyengar-Krause. Or if you look at the stable category of finite complexes or finite spectra, in that case, I have the work of Hopkins, and Smith, and for the cosupport, Strickland, Tobias Strickland. And just to make a connection with the first talk that was by using a Morales theories. Right? In that case, in fact, they work with Ian local spectra, and then the cosupport, you look at the ends and such that when you look at elements that is different from zero, just to make a connection with the first talk and Morales theories. Right? So there are many examples of these functions in the literature. So, okay, but there is in all the cases the topological space X is different. Right? Here you have the spectrum. This X is the spectrum of the ring. Here you have the X is the spectrum of prime ideals of the homology of the ring. And in fact, this is a bit more in a more general context with when the tensor theory category admits an action of a graded ring, and then the corresponding X is the homogeneous ideals of this ring, and here you have this. Right? So you have different, for each example, there is different X in which you have a support functions, and in these cases you end up having this is a bijection, so you can parameterize uniquely your localizing and colocalizing subcategories with subsets of X, and you can, given a subset of X, you can reconstruct. There's a way of constructing the category. But let me have a more general context now. So now I'm going to assume that T is essentially small. And in that case, there is a construction by Balmer, which is the Balmer spectrum. And the Balmer spectrum will consist of all prime thick ideals, or thick prime ideals. Yeah, well, I don't. And prime is what you imagine it is, so if you have A tensor B in P, then either A or B is in P. So this is as a set, and then there is a topology given by the following for each object T. You define the support of this object to be those primes which do not contain this object. And this forms the basis of closed sets. Closed sets for the topology. So, and let me just recall that a Thomason subset is a union of closed subsets. Is it visible? Of closed subsets, each of which has a quasi-compact complement. And then this topological space is just built from the category itself. Right? It's not something that you look somewhere topological space which fits nicely with your framework. It's like something which is built using the structure of the category itself. And then There is a Balmer's abstract classification theorem, which says that using this topological space and defining a support function, you have, I should write radical, well, let me just simplify, okay. Radical thick ideals with Thomason subsets of SPC, and then it says that this is a rejection. So you can use this space to parameterize using certain subsets the radical big tensor ideals in here, right? And well, in our case, if the category is rigidly compactly generated, then just in that case, you have the compact objects and the dualizable are the same, and then you can erase radical from the picture, right? Okay, but that only is for essential. Sorry, here I'm working in the essentially small context. Sorry. But that's a situation in which if T is just any tensor triangulated category, and you look at the small objects, the compact objects, for which for one's C dash preserves colimits. In that case, this is essentially small. So it makes sense to look at the Balmer spectrum for the small objects, for the compact objects. And the idea is just not only to look at compact objects, but to see if one can parameterize the localizing and colocalizing ideals using this very same topological space that choose to classify the thick ideals for the compact objects. Okay, so and now I have to introduce some definitions. I take a prime in this topological space, and I say that this prime is weakly visible if this prime can be, as a singleton, can be described as the intersection of Thomason subset and the complement of a Thomason subset, where Thomason subset. And in this situation, Balmer and Favi, they construct an idempotent in the category. In this situation, there exists an element, an idempotent associated to this prime ideal. There exists an idempotent which is constructed by, well, the idea is that this, for each Thomason subset, you can split the unit, you can construct an idempotent triangle. And in this idempotent triangle, there are two idempotents, and then you just combine them to produce this idempotent for each prime that you can isolate as the intersection of the Thomason subset and the complement of the Thomason subset. And so we will say, in this case, we will say that this topological space or this spectrum is weakly Euclidean if is weakly Euclidean if each prime is weakly visible.
So what was that property that this idempotent has?
Sorry?
Could you say what the property did? Or
Yeah.
What's the property that?
Yeah, exactly. So the support, we will construct a support function using these idempotents, and the support of this idempotent will be this single prime.
Oh, okay. So it's an idempotent that has.
Yeah, that detects that the support will be just a single prime. And then, yeah, it goes in the work of Barthel-Heard-Sanders that they define a support function. I mean, here we already have a definition for the support of compact objects that comes with the spectrum, with the Balmer spectrum. Yeah, it's these basics of closed sets are given by the support of compact objects, and that's the definition. And then using these idempotents, you got a notion of support for the rest of objects. So you have these are going to be these primes such that this is not zero. And then in this joint work, we introduce the cosupport by taking those primes such that ohms from these idempotents are non-zero. Okay. So let me say a few things about how they behave. And now it's time for other things.
Alright, we'll leave it there, then it's
So now I will just describe some properties of these two support functions and cosupport, but somehow I mean, philosophically, cosupport is also a support in the sense that it detects some properties of your subcategories, but they are different. But they are close and the different structures.
Sorry, I have one question. So, say I take this example of compact spectrum, and what would be the GB is idempotient in this case? Fix the height.
It should be.
It's basically a finite version of the monochromatic layer.
So would it be the Ln local sphere?
No, the monochromatic layer.
But that you can't. That's not a smashing localization. Does that matter? Maybe it doesn't matter. Oh, okay.
It is smashing, but it's not a localization. The monochromatic layer is smashing, but it's not a localization, and these GPs are also not
layer,
localization.
right?
Yeah, they are a combination of two idempotents. So, but they themselves they are not localization. Yeah, maybe I was too fast.
So it's the
This
fiber of the Ln local sphere to the mapping to the
LNF.
Ln-1 local sphere.
The LNF local sphere.
The Ln local sphere mapping to the Ln-1 local sphere, you take the fiber, and that would be your G.
LNF local sphere, though, the finite localizations.
Oh, okay.
Yeah, but yeah.
So, yeah. So now we have this.
Okay, okay. Does that do a specific construct? This is a purely abstract result, no? So this says it always exists. This isn't okay. This isn't never mind.
It is constructive.
It is constructive. Okay.
Yeah. Okay. So, for example, one can look. If you look at the support of this idempotence, you get the prime itself, but that's not. But when you look at the cosupport, at this idempotence, this is could be potentially bigger than of P, and then this goes Q. Such that contain P. So here is a first difference, and it's related to this kind of lack of symmetry. The way that the idempotents are constructed, they behave well with the monoidal structure, but it's different when you look at the internal ohms. That means that you could have P and Q, and Q containing P such that the internal ohm is non-zero. And but nevertheless, there is an object, but you have objects which cosupport is just a single isolated prime, so you can look at GP, and this is just. So now I'm going to give some names. So. So this is going to be just tensoring with the idempotent, and this will be just taking ohms, internal ohms, and then I will define what we call the stalk of T at a prime to be just the image of this function. So I'm going to call it this way. And the costalk at this prime. Yeah. Okay, the real image of this one. Okay. And another difference that I wanted to point out is that the support of the unit is everything, but the cosupport of the unit behaves very differently. It doesn't need to be everything. But there is one object which is the object that works well with the cosupport is the Brown-Kamenev duo for the identity, and in that case the cosupport is everything. But the cosupport of the Brown-Kamenev duo is everything. So the support is better behaved in that sense like that, the cosupport. Okay, so now, what we are looking at, here, so we have here parts of this topological space, and we have these functions, we have localizing ideals in T, and then here we have the colocalizing ideals in T. And the question is whether this these functions, which I want to call is that Balmer-Favi support introduced by Barthel-Heard-Sanders, and then the Balmer-Favi cosupport, these specific ones. And then you want to know when they have bijections. You have to check when you have a bijection, when really these parameterizers all localizing ideals or all colocalizing ideals, or when for each set of parameters you can reconstruct a unique localizing or colocalizing ideals. Yeah. But this is the parse of a set. Yeah. So you have some special subsets. You have the empty set, for example. So you take the empty set. Right? If you expect this to be a bijection, the empty set should have only one localizing ideal which support the empty set, and one colocalizing ideal to support the empty set. Right? But in the actions for these functions, you already have the zero, and zero is a localizing and a colocalizing ideal. So if you expect to the bijections, what you expect is that only zero has empty support and only zero has empty support. So let me write a definition maybe. When I write if I have a subset, these are all the objects such that the support sits inside Y, and the same for the position. Okay. So if you want this to be a bijection, so the first thing you need is that this is 0 and that this is only 0. There are no other objects which have empty support or cosupport. And we are going to give a name. When this happens, we'll say that the detection property holds. And when this happens, we'll say that the co-detection property holds. So this is just the first thing that you need to check. Yeah? Otherwise, you're not going to have a bijection. Okay? And well, now, and now we have the empty set, and the next thing you have are the singletons, right? And there is nothing in between the empty set and the singletons. Right? So this is, and the singletons, yeah, correspond to, well, those objects that the support is T, or containing T. It could be empty, but we said that 0 is the only that has support empty. We're assuming now that this property holds to keep on going, right? And the same for the cosupport. So what we want essentially is we want that the preimage of the singleton and in both functions you want to be minimal. Minimal in the sense that between 0 and this, I didn't say anything, but the properties of the cosupport, they ensure like that this is localizing and this is colocalizing ideals. Okay? So from the properties we know that they already differ, localizing and colocalizing ideals. But if you write the singleton here, they should be minimal. There should be nothing in between, because there is nothing in between the empty set and the singleton. Okay? So the next thing you need is that this is to be minimal here, colocalizing coideal and localizing ideal. So this is what you need. And it turns out that you can compute explicitly what they are, And the detection and the codetection property, they adjust the stalk and the core stalk at the prime. Okay? So, and they just coincide with, assuming, now in 2 we are assuming the detection and the codetection. So this is the stalk and the core stalk. So if you want any hope of having a bijection, next thing you need apart from the detection and the codetection is that the costalk and the stalk are minimal localizing and colocalizing ideals. Right? And to check that something is minimal, in the work of Benson-Iyengar-Krause, they develop a criteria in terms of the ohms between objects in the category. So you have a criteria where you can use to check when something is minimal.
For localizing ideals.
For localizing, yeah, sorry, yes, for localizing ideals. Yeah, you are correct. So now we have, and now just, so we need this, and then we need this, yeah, and then for the first thing that you need is that, well, now when you group together, when you have several primes, you have several options now here. You can just glue together the stalks and look at the localizing and colocalizing ideals that you can build out from the stalks and costalks, or you can just take these two, right? But they should be the same. So, and then you need some gluing principle that tells that there is a unique way to glue the information at each prime. Right? So, and then this is the local to global principle, which essentially says that, let me write it for the Cosupport, but if you look at the colocalizing ideal generated by one object, that's something that you can reconstruct from the image of each object and each of the stalks at each prime for each for each prime, sorry, in the Cosupport. Okay. So these are things that you need, yeah, and well, the local to global you just replace loc with and then in the work of Benson-Iyengar-Krause in the context of tensor triangulated categories, they show that these are with these conditions you have a bijection. So if you assume in that case you had detection and codetection, but if you have minimality and local to global principles in this sense, and the unique way of gluing, then these functions give you a bijection. So, and how are they related? And it seems that all this information is relating among themselves. The detection and codetection properties and the local to global principle are not independent among themselves. So let me write some diagram. So you have that for detection for the support holds if only the local to global principle. holes, and we found with the colloquial global principal holes. And then co-detection implies detection, but not the other way around, and this is given by an example by Greg Stevenson, which I failed to mention in my last talk.
Does not imply.
Sorry? Oh, sorry, yes. I was getting wrong. So, yeah. And an important result is that in this very general context, costratification implies stratification. And costratification means that the cosupport function gives you bijection, and stratification means that the support function gives you bijection. So, but the point, I think, that all the examples that we know that they are stratified, they are also co-stratified. I think that's correct. That we don't know an example which is stratified and not co-stratified. So we still don't know. And in particular, if these co-stratified, there is a bijection between localizing ideals and colocalizing coideals. So that you have this bijection. By just taking the orthogonals. So this gives you something stronger than just stratification. This is stronger. And then, and in that case, there are nice relations between the orthogonal and how they are reconstructed from these functions. But maybe I will just jump some of the formulas I wanted to give and tell you a bit about how these properties behave with respect to functors. So assume that you have now, we have T and S are categories in this context, tensor triangulated categories, T and S. And this is a coproduct preserving functor. And it has right adjoint. So this is this right adjoint. And then I will use this notation for the corresponding map between the Balmer spectrum by taking the images. So you would like to know how these properties, they move around functors, so you can just develop some techniques so that you can get stratification of classification and costratification of one category by comparing with another through one of those functors, these nice functors. And for example, you can say a few things. So, for example, you can say that the image of this functor is just the support of f star of the unit. Yeah. So you have several formulas, or just if this functor or this is the right adjoint to this joint. Yes. So this is the right adjoint. So if those are conservative, then this map is subjective. This is the mapping spectrum, and you can get information about these from the properties of the function. And so now you make a choice. And the point is, how do you, so we know that costratification implies a stratification, right? And you would like to know how far are from stratification implying costratification, right? So now I will give you a theorem which somehow compares this through some of these geometric factors. So you, what we call the bootstrap theorem. So assume you have one of those factors with this hypothesis as before, and assume that A T is stratified, B is that S is costratified, and that this functor is conservative. So under this hypothesis, you know that T is costratified. So that means that the only thing you need to show that, assuming that T is stratified, what you need to show that T is costratified is just to find a functor, a conservative functor into something which is co-stratified, and then automatically you have costratification for T. Right? And let me give you some examples. So this general setting allows you for using different strategies depending on the context, on the category you are interested in. So if you are in an equivariant setting, just going to fix points, yeah, it would be a strategy. If another strategy, if you are working with a regular ring just going to residue fields, and depending on the context, you will choose there will be a natural functor to work with. And then I will just briefly tell you some examples. Well, there is one example which I particularly like. So it comes. I'm kind of unstable multiple theories from birth, so I like to have a topological space in the lecture. So it's a good connected topological space such that multiple topology is repeated. And you can look at the category of modules in the category of the stable category is spectra, which are modules over this ring, and by this I mean the functional spectrum from the suspension spectrum of X into the Balmer-Favi spectrum for FP. Right? And so in that case, the following are equivalent.
What does P good mean?
P good, yeah, okay. So you have the Barthel, there's a factor which is the Barthel P-completion. Good question. The Barthel P-completion. So it's a factor from a spaces to spaces which turns homology equivalencies into homotopy equivalencies when you P-complete. And P-good means that it comes with a map from X to its P-completion. P-good, that means that this is a mod P-homology isomorphism, that when you P-complete, you don't change the mod P-homology. In principle, it would happen. And then it's P-lat. So the following are equivalent. This category is a stratified. This category is costratified. And the third has to do with a category which is built out of the cohomology of X by looking at cohomologies of elementary abelian P groups, maps from these cohomologies into cohomology of elementary abelian P groups. So there exists a category which is Rector's category built out of elementary abelian P groups, and with a map into co-change of elementary abelian P groups. And then here we have for each elementary abelian P group in this category. So if this map induces a conservative factor, induces a conservative factor from E. Yeah, so it's I think I got it the other way around. I want to put this factor from the modules. Now I'm confused about the covariance and contravariance.
It's like an induction factor, right?
Yeah, but it's the induction, not the restriction. Sorry, I was confused about the laws. Yeah, exactly. Yeah. So, if induction of the modular structure along this map is conservative. And one example that came from a previous work is that we got this example in which X is the three connected covariance of S3, in which we could not prove that it was costratified. So it was a potential example of something that is stratified and not costratified, but turns out that it's not. That this works for this example. And then just other examples. You have R, a regular Euclidean ring.
Sorry, and you know a bunch of examples where that is actually conservative, so
Yeah.
so this is actually
Yeah, for finite group, this is kind of a Schulinar's condition from representation theory. There is one example in which we don't know, it's kind of crucial somehow, is when X is the classifying space of a discrete p-total group or p-total group. It's not, this is an example in which we do not know.
like, for instance, if it was a free loop space in BG, for instance.
Free loop space on BG. Oh, but this is, that's the splits like BG and G, right? The free loop space on BG.
This is a section?
There's a section, yeah.
With H spaces or something.
Yeah, for H spaces,
H
yeah,
spaces
for H spaces
many
it works,
examples.
yeah. But for
Well,
H spaces with finally generated cohomology.
Yeah, we need to see here.
Yeah.
Okay.
So, yeah, you can look at this table, module category, for RG. And then this is also costratified by using, and the idea is that just by reducing from RG into, you just take the residue fields. Yeah, you just looking at the for each price. You just look at the reducing from R to its residue fields, and this is a factor which has been studied, and then you know that this is conservative when you go through the different residue fields for the primes in the spectrum. And just another example that I wanted to mention is, so if G is a finite group, just to give different situations in which you have naturally such a variable. So if G is a finite group, and then you have an algebra object in equivariant G-equivariant spectrum, then if you assume, well, you need to know that the Balmer spectrum for when you look at the direct category for the fixed points for the subgroups and the compact, this is invariant. And then you have to look at each of these fixed points, and then when you look at the fixed points, this is costratified. Then, yeah, when you look at the E modules in this category of G-equivariant spectra, then this is also costratified. And for this, we use another. You need another joint work with Barthel-Heard and Naumann and Cosupport. Yeah? But so in this kind of situation, it unifies several strategies in the literature, like reducing to the residue fields, like looking at geometric fixed points, and here is kind of a detection by subgroups. Right? So I wanted to just maybe show quickly 3 different strategies, situations in which you can apply this very general theorem. So essentially it tells you that if you are stratified, all you need to do is find a conservative factor into something which is costratified. That's the abstraction. Okay, so sorry for going.